Hello everybody. In this video we're going to be covering section 12.6 reaction mechanisms. This is going to be an important section for us. In particular, if you're interested in continuing on with organic chemistry, getting the broad strokes of what a reaction mechanism is and how it works is going to be important, so you'll want to pay special attention. For our learning objectives, we're going to distinguish net reactions from elementary reactions. We're going to identify the molecularity of an element of elementary reactions. I always struggle a little bit with that word. Write a balanced chemical equation for a process given its reaction mechanism. So we're going to figure out how to go from reaction mechanisms to balanced chemical equations. And we're going to derive the rate law consistent with a given reaction mechanism. So first off, what are reaction mechanisms? Basically, reaction mechanisms differ from the overall chemical reaction in that they're giving us more information. All right. And basically what winds up happening is in a net chemical reaction, we're only seeing the beginning reactants and the end product. We don't know how it got from one to the other, and typically there's going to be more than one pathway you could imagine for getting from a specific reactant to a specific product. But a reaction mechanism provides details regarding the precise step-by-step process by which a reaction occurs. Okay, which bonds were broken, which ones were formed. Each of the steps in the reaction mechanism is what we call an elementary reaction. Elementary reactions are explicit representations of the chemical change taking place. Okay? They're depicting the bonds that are breaking and the ones that are being made in order to yield our products. The rate law for an elementary reaction may be derived directly, so that's a big difference from a net chemical reaction. We weren't able to derive the rate law directly from those, but if we know the elementary reactions, we actually can. And I'm going to show you in just a little bit what that looks like. So let's go over a little example here. Okay, let's consider the decomposition of ozone. All right, it has two elementary steps. In the first one, this O3, three oxygens bound together, is going to break down into an O2 molecule and a free oxygen atom. Then one of these free oxygen atoms is going to go and it's going to bump into an O3 and it's going to form two O2 molecules. All right, it's going to take one oxygen from this guy and it's going to form two O2s. All right. Now there are a few different ways this could have played out, right? It could have been true that this free oxygen atom actually bumped into another free oxygen atom and formed an O2, and then these were always breaking down. But we now know, because we have this reaction mechanism, that that's not the way it plays out. We get a free oxygen atom and it actually bumps into an O3. All right. An important thing that's always going to happen is that if we sum these together, like we've done in Gen Chem 1, all right, we cancel these spectator guys here, all right, it's going to yield the overall net reaction chemical equation for the reaction. Okay. Now I mentioned these spectator guys here. Okay, these free oxygen atoms do not appear in the overall reaction. Okay, they're produced in the first step and they're consumed in the second step. We call those intermediates in this when we're talking about kinetics. Okay. So let's start talking about unimolecular elementary reactions. And first we need to talk about what is molecularity. The molecularity of an elementary reaction is the number of reaction entities, atoms, molecules, or ions. Okay? A unimolecular reaction, therefore, involves a reaction of a single reactant entity. Okay, so if I just have A here and it's going to go and produce products all on its own, that is unimolecular. There's only one reactant entity. The rate law for a unimolecular reaction is first order. Okay, what that means is that if I know the elementary reaction here, okay, and it's unimolecular, the rate is just going to be a first order rate that depends on A. Let's look at an example of that. Here we have the gas phase decomposition of cyclobutane, okay, to produce 2 ethylenes. This is a unimolecular reaction, and it is both the overall reaction for it and an elementary equation. Okay, it's both of them. All right, there's only one step, and it only involves one molecule. Now, because this is the elementary reaction, before we wouldn't have been able to simply say that the rate is equal to K times the concentration of the cyclobutane. Okay, but because we know that this is the way that this goes, and it's just a simple elementary equation, we can now make that claim directly. All right. A bimolecular reaction involves 2 reactant entities. So we're going to have A plus B to go to products, or just 2 of the same molecule that are going to go to products. And their rates are going to look like this in this case. Okay. Some chemical reactions occur by mechanisms that consist of a single bimolecular elementary reaction. Okay. In this case, again, the overall balanced chemical equation is the same as the elementary equation, in which case we can directly say that the rate is equal to K times the product of these 2 concentrations. All right. That's only because we knew that that is the case here. So basically, in these last few examples, what we've done is had a very simple system, okay, where our reaction mechanism is a single elementary equation that is itself the overall equation. We're going to talk about what we'll do when things get a little bit more complicated here when we start talking about term molecular elementary reactions. Okay, now these are very rare, but there are some documented reactions that require the simultaneous collision of 3 molecules. All right, now you have to imagine that it is not very likely that 3 molecules are going to strike each other in the proper orientation simultaneously. Okay, that's just a less probable thing to happen, but it does happen. An example here is where we have nitrogen oxide colliding with an oxygen molecule to form nitrogen dioxide. In this case, again, we have this elementary equation that is the same as the net equation, and we can say that the rate is equal to K NO squared and the concentration of times the concentration of oxygen. Let's talk about what's going to happen when that's not true. Okay? When that's not true, what we need to start thinking about is which is the slowest step. Okay? It's often the case that one step in a multi-step reaction mechanism is significantly slower than the others. The slowest step is called the rate limiting step, or rate determining step of the reaction. The rate of the overall reaction will be determined by the slowest step. So here we have a reaction mechanism, okay, where the first step is quite slow and the second step is quite fast, okay? So long as this is significantly slower than this first step, I can basically negate this. This isn't going to slow down the rate of the reaction at all, not any significant amount. In that case, I can derive the rate law by going to just the slowest step and deriving the rate law from that one.